How's it going, everyone? Welcome back. Apologies for all the craziness that happened today. We didn't actually get to do a lecture or a lab. So just to clarify, there is no lab 9. We're only going to be doing the lab that corresponds to the buoyancy lab, which is lab 10. Just to kind of get you guys on track. If you guys see this video before we meet on Thursday, we have the review on Thursday, so there's no lab. We're gonna have the exam next Tuesday, so there's that. Then after that, on Thursday, we're gonna have the last lab, lab 10. And then after that, we're gonna be having the review on Tuesday, the next Tuesday, and then the final. And so what I'm planning on doing for the actual final, because everything's like coming quick, um, for the review for the final, I'm gonna have that final review exam up the week before, so you guys can actually see it and work through the problems. When we meet up on Tuesday, you guys are already gonna have some type of understanding and, well, not understanding, but idea of what to expect. And so that's gonna be there. So when we meet up on Tuesday, we're just pretty much covering the problems, and you guys can cross-check what you guys got right and wrong. And hopefully by that time, you guys are already aware of what's going to be for the final. But of course, that's jumping the gun. Right now, we have to focus on the second exam. And so today's topic is on angular momentum, but it deals more than just angular momentum. It deals with like every type of rotational situation you can think of. So I know we've already covered some type of rotation, which will be really useful for this chapter. Everything that you can think of in a linear fashion, you can conceive it as a rotational counterpart. So for example, we talked about position, we talked about velocity, we talked about acceleration, and I showed you guys its rotational counterpart. For position or displacement, we use theta, which is an angle. So angle is a rotating distance. Like if you think about it, the angle of something is a rotating distance. It's an arc. If we talk about velocity, then we can see the counterpart, which is angular velocity. And then like with acceleration, we can think about its counterpart, angular acceleration. So then we talked about torque, how torque is a rotating force. Uh, and I think that's as much as we covered. So now we're going to be diving a little bit deeper now. So let's jump into the whiteboard or the OneNote, and then we're going to get into this week's new material and hopefully familiarities and ways to associate everything we're going to talk about today. So like with force, we have mass times acceleration. And so torque is defined. We talked about torque in terms of force cross radius, right? Because you have the distance from where the force is at that's causing that. You can also define force in a different way. If you erase this and we just look at what torque is, if you were to change each of these terms into its rotational counterpart, it would give us the same units. It would still be the valid equation. And what I mean by that is we know what torque is, rotating force. We already know what acceleration is. It's angular acceleration, right? So the last piece of the puzzle is mass. We haven't talked about mass as a rotating quantity. And so I wanted to start this off by talking about this, because then everything that follows will rely on this rotating mass concept. So rotating mass is something we call inertia, and we define it as a capital I, inertia. So essentially this equation also equals to torque, aside from force cross distance. And the reason I brought this up is because we're going to be using this for converting momentum to angular momentum, but more than anything to touch up on this idea of inertia. Inertia is just rotating mass. So anything that's rotating has inertia. And when you think about mass that is rotating, we can just think about it in terms of inertia instead of just mass on its own. So one way to think about inertia is to think about a person rotating. So I'm right here. And so if I start rotating in a circle, however you may want to interpret that, if I rotate around a certain axis, like right in the middle, so let me just insert this right here. So if I start rotating around that dark line, let me change the color of that. Let's go with this color. So if I start rotating around that axis, I'm going to have some type of inertia. And so inertia helps us understand a little bit more on how physics works, because how do I want to start this off? When we look at certain phenomena and we see that certain aspects of an object change, we want to understand how this phenomena occurs. So let's get into it. To understand this, we want to define what inertia is. Like, we know it's a rotating mass, but can we break it down? And so we can. Inertia for a point mass, meaning something that doesn't take a lot of space up, we can define as m, so the mass of the object times its radius squared. And so this is what defines inertia. The reason why I say for a point mass is because depending on the shape of the object, this moment of inertia can have a different coefficient. So what coefficient means is just a value in front of the mass. And I'm going to get into that in just 1 minute, but I want to explain this whole situation first. So when you have inertia, you want to focus on the matter that consists of this thing that's rotating and its radius, how far this object stretches on either end from this rotating axis point. In this case, the moment of inertia, the axis point right here is that red line, and it stretches out from here all the way to the arm, and from here all the way to the arm. So you have a radius. If my arm is 0.5 meter long on both ends, then if I were to ask, hey, what's the inertia of the person rotating like this? Then we would just plug in the mass, and then we would plug in the 0.5 meters squared. So if just say the mass was 50 kilograms and the radius is 0.5 meters squared, then we're set to go, right? Like, you just plug it in and you find what the moment of inertia is for this object, for this person. Okay, so then we want to get into the progression of why this is important. And I'm going to start off with this example, not this problem yet. So let me move this problem down. We're going to get to this one eventually. Think of a figure skater. Have you ever seen a figure skater who starts rotating? And then, like, first they have their hands stretched out. So that means their moment of inertia with the radius being longer, because from here to where my arm stretches, that makes my radius longer. That means I'm going to have a bigger moment of inertia. if that figure skater brings everything together, that radius decreases. It gets smaller because now instead of having, so I'm going to copy this whole image. Oh, it doesn't. Let me use this. There we go. Copy. And I'm going to paste it right here. So now, if this figure skater, instead of keeping their arms stretched out, they bring everything together, that means that the radius isn't half a meter anymore. It's still rotating right there, right in the middle. But if their arms are all together, so I'm just gonna like put two arms kind of close together, the radius has decreased. So now their new moment of inertia would be 50 kilograms times, just say whatever the length of your torso is, like split that in half, and we can end up with like 0.1 meters squared. And so what this tells us is that the moment of inertia, when you have everything closer to the center with a smaller radius, you have a lower moment of inertia than you do when you have your arms stretched out. What is it that we notice when the ice skater is spinning and then brings everything together? What happens to their speed? And so you guys can put the comments in the chat. What happens is, if you notice, the speed starts to increase when the figure skater brings everything together. Hopefully you guys can hear me. I don't know how far this is. I'm just trying to get it out of the view frame, but hopefully you guys can still hear me nice and deliciously. So when the figure skater brings everything together, as they're spinning, they start to increase their speed. And what's really interesting about this is that we've already talked about how changing your speed is an acceleration. And so if the figure skater goes from this to this and changes speed, but there aren't any external forces, then how do we explain this change in speed or this change in velocity? And that's where we have to introduce a new concept. Inertia is this keystone foundation to this idea, but we need some other type of tool to help us understand how it is that the velocity changes of this figure skater as they bring everything together, and it's related to inertia. So let's move this lower. I should have just put this all the way down because we're still going to need some space. So this leads me to this new concept that relates to inertia. I mean, you can relate everything to inertia. You saw how we related torque to inertia. So the last topic from last week that we covered was momentum. I'm sure you guys already know where we're going with this, but I like to story tell it into its format. Momentum is defined by the mass times the velocity. We've discussed that. We talked about conservation of momentum and how objects can transfer their momentum to another object and vice versa. And this concept can also be related in a rotational fashion. And this is one of the big keystones to this situation. So angular momentum is defined by a capital L. Don't ask me why. So we can relate it two ways. We can relate it to the old definition of torque. So by that, what I mean is, I'm going to just draw a line. We know torque is equal to force cross radius, right? That distance from where you're pushing something is a torque. If you look at angular velocity, you can apply the same idea. What is the linear counterpart to torque? Force. What is the linear counterpart to angular momentum? momentum, and then cross R. So what this means is if we draw a circle, so let me get this circular thing right here. Check it out. We're looking at this from above. So we're like, it's like, think about this like an orbit. There's something in the middle right here. And if this object is moving at a certain speed, it has momentum, right? Because velocity times mass gives you the momentum. Now, to find what the angular momentum is, we just need to know what the radius is. And the radius is from here to that point, that distance, that radius of the circle, or any type of circular orbit or motion, you just get that radius. And so whatever this radius is going to be some type of R. And this is velocity. They're two different. This is R, not V, because my R's kind of look like V's. So if we multiply this times mass, we can get momentum. And we know the radius. So then we can find what the angular momentum is, right? So this is one way of defining angular momentum. We can just look at the rotational counterpart with torque and apply it to the same way. Or we can do what we did to torque earlier on, like this. We can do that too. So both equations are applicable. You can use either of them. And I highly recommend, when talking about any type of matter, when in questions that you get, whatever information they give you, if they give you the information, if this is an angular momentum problem and they're asking for, or they give you linear momentum and you know the radius, you're going to be using this equation right here. But if they give you the information in different terms, if it's suitable for another version of angular momentum, use that instead. And I'm going to show you what that equation is. You guys can maybe already figured it out. What's the counterpart of mass? It's inertia. What's the counterpart of velocity? It's angular velocity, omega. Let me rewrite that because it looks ugly. There we go. And so this is a way of writing angular momentum. You can use either or, but for the figure skater problem, this one is what we're going to use. It helps relate inertia to some type of spinning factor, which is angular velocity. And so if we look back at this problem, we know that the moment of inertia is higher when the person has his arms stretched out and smaller when the person has their arms closed in. Okay. And so to understand why the speed increases when they come closer, even though there isn't like a external force coming into play, we need to talk about something called conservation of angular momentum. And so this concept is really crucial to this. And we've already talked about many different types of conservation ideas. We talked about conservation of torque. I mean, no, we we talked about conservation of momentum, conservation of energy. Yeah, not torque. My apologies. But we can also apply that to conservation of angular momentum. It only makes sense because if there's conservation of momentum, just by changing something to a rotation, that law should still apply, or that principle, I should say. So we have that idea. And what that means is what happens before and after a change in inertia, the angular momentum should still be the same. What does that mean? Let's take these two examples. You have a moment of inertia in the figure skater. After the person brings everything together, their inertia changes. Though their I can't talk. Though their inertia changes, their angular momentum should still be the same no matter what, because there was no external force that came and took away some of that moment of inertia, or I mean, sorry, that angular momentum. So that means, so you see the first case, I didn't put a little line right here as I did for the second one. So we're gonna, let me just call this 1, and this is gonna be second. Once I can get my mouse to like focus. It's like lagging. Okay, so first case, second case, this is all within the same event. It's just different moments. And when you do conservation of momentum, the best way to look at this is to look at everything that happens with one given situation of inertia. And then the second case is once the inertia changes. And so that's a good way to look at how you want to apply conservation of inertia. So inertia in state 1, and then inertia in state 2. Okay, so this is getting hot. I'm gonna take this off. Even at nighttime, freaking this weather is crazy. So what this means for these two cases is that the angular momentum during the first case of angular inertia, sorry, has to equal to the second case. So that means if there isn't anything acting on it, the angular momentum has to conserve. So what is the definition? We know what the inertia, moments of inertia are if we're given that information. So we want to jump into this equation. That was this one right here, you guys. And not this one, because there's no inertia in this one, right? So it just makes sense to use the first one right here. So I'm gonna do that. We have I1 omega 1. That has to equal to I2 omega 2. Because the total moment of inertia in one case has to equal the same at the second case, even though, angular momentum has to be equal, even though inertia changes. I keep interchanging those two words. My apologies. As long as you're following this to here, you're on the right track. So we don't have exact values for this. I mean, we actually technically do if we plug it in. So let's just do that. Actually, that deters from the whole idea, because all we want to understand is that the value is smaller at the second case than it is at the first. So I'm gonna give, actually, let's just do it, because I think that's gonna help a little bit more. So first inertia is 50 times 0.5 squared. Don't forget to square that. And so that gives us 12.5. So we know what the moment of inertia is for the first case. 12.5. And so the units, as you saw, were kilograms times meters squared. So I'm not going to include those, but I just want to let you guys know what the units are. Just say we know that we know one of the angular moment, we know one of the angular velocities, we know the first one. And so let's say angular velocity is 5. And here we talked about what the units were for angular stuff. It's radians per second. So remember how we talked about theta? It's not in degrees, but in radians, it's just radians. So you can replace radians with meters if it was a linear situation. And so the same thing with angular velocity. Angular acceleration. It's 5 radians per second squared. It's just linear counterpart. So these are the units. You're gonna sometimes see these units differently. And I have an example that gives you these components in different units. And I'll show you guys what the difference is and how to convert. So you're gonna wanna keep an eye on that too. So if the angular velocity for the first case is 5 rad per second. We've already discussed how the velocity changes. Velocity is related to angular velocity. So the faster you're spinning, the higher the velocity, right? So the angular velocity is higher too. We talked about this first case and how once the arms come closer, the velocity increases. So we should get a higher velocity for the second case than for the first. So what this means is that for omega 2, we should get a value greater than 5 rad per second. I keep trying to write it neat and then the lag just screws it all up. So we need to get something higher. And if we do the math and we end up getting something higher, that means conservation of angular momentum shows us that the angular velocity does increase. And then I'll hit up on another point. So waiting for this mouse to obey my commands. So then omega, moment of inertia, I was like, all these terms, just confusing them. Moment of inertia for the second case is 50 times 0.1. So instead of 0.5, it's just 0.1. And so that is a smaller number. It's 0.5. Okay, and then we don't know what omega 2 is, but we're trying to find out, and we assume it's greater because we see that in figure skating competitions, a person brings their arm closer and they start spinning faster, and so we want to see if that's true. Actually, let's just do this. Okay, get all that away from here. We're almost done with this. So all we have to do is just divide 0.5, 0.5, cancels. So then 12.5 divided by 0.5 will give us 12.5 divided by 0.5. And we get, it's a pretty big number, 25 rad per second, omega 2. So it's 5 times faster. By bringing your arms in, at least in this case, might have been an exaggeration, but the person was spinning 5 times faster when they brought everything together. And so this helps prove or show that there's this new concept that can explain how you can change your velocity or your angular velocity without having an external force on there, or like how you can explain that. Because think about it, a figure skater, they start getting closer together and start spinning. It's not like somebody is spinning them faster. It's all because of the moment of inertia. This moment of inertia changed. And so what this tells us is that here's how to relate inertia. The bigger the moment of inertia, the slower you can go. The smaller the moment of inertia, the faster the faster the tendency you have of moving. It's like that with Newton, with his laws, how, like, I don't want you guys to memorize the laws. I just want you guys to know how to apply all of this information, because that's redundant. I care about you guys understanding how to apply all of this. But with inertia, if there's a heavy object and you try to push it, it's hard. It resists motion. And so when you try to push on it, it's a lot harder to get it moving. That's because it has a high inertia. And so that's why the inertia here was higher when the figure skater had their arms like that, and then smaller when they're like that. So naturally, since they have a smaller inertia, they can spin faster. And that's how this figure skater is able to get their angular velocity to increase. They use the laws of physics without even realizing it. to increase their speed. They change their moment of inertia. And we can prove this with conservation of angular momentum. So that's part of it. We're gonna do some examples, and then there's another topic to discuss. So we're gonna do this problem first. I thought we are gonna do it the other way. We're gonna do this one right here. So I'm gonna show you guys how to apply this concept into maybe something similar that you might get in your practice quiz. But technically, this one's a little bit harder, but I'm doing this on purpose because I want you guys to understand how to do this. Even if you guys don't follow along, like it's just hard. Once you guys do the practice quiz and take the quiz, come back to these type of problems. They're gonna be really useful. So let's bring this down, because this is going to use a lot of these concepts and more. Okay, let's read this problem. 3 children are riding on the edge of a merry-go-round that is 100 kilograms. So the merry-go-round is 100 kilograms, has a radius. So they give you the radius, 1.6 meters. So think about the merry-go-round like the person outstretched. Their whole radius from the center to the end is 1.6 meters, and their mass is 100 kilograms. They give you how fast they're spinning, but do notice the units. So they tell you that this merry-go-round is spinning at 20 RPM. And you might be like, like you might, if you have a car, you know what RPM is. You see that in your car when you're revving up, it is revs per minute. That's where revs comes from, or that idea when people are like, rev up your engine. But we'll get to that right now. Let's finish the problem. So then the problem says the children have mass. Okay, so there's 3 children on that merry-go-round, and they each have specific masses of 22, 28, and 33 kilograms. If the children who has mass 28 kilograms moves to the center of the merry-go-round, what is the new angular velocity and RPMs? So here's one thing to understand. When your answer needs to be in not standard units, so standard units would be rads per second. If instead they want the answer in RPMs or any other type of angular velocity unit, you don't have to convert whatever you're given. If it's in the same units that the answer needs to be in, you don't need to change anything. So I hope you guys got that. If you're given RPMs, don't convert to rad per second and then change it back to our revs per second, because the answer needs to be in revs per second. So the answer should come out in revs per second. If we did this problem with the ice skater, if we had it in revs per second, you would see how everything cancels out but revs per second. So your answer would have still been in revs per second. Likewise, the same here. So what are revs per second? Before we even jump into this problem, let's talk about that. So revolution per second. Wait for this thing to eventually this mouse will start working. Rev per second. Whenever you see the word per, it's like miles per hour. The per is just like, it tells you it's a fraction. So revs per second. So how do we convert from radians per second to revs per second? So seconds is the same thing. So we should just focus on revs and radians. What's the difference between these two? Because then the next problem we're going to do relates to this in a whole different way. So revs, so radians, okay. We know radians going a full circle is 2 pi. So we already have 3 types of units for like angular distance. We have degrees, we have radians, now we have revs. And a rev, the easiest way to look at this is that a rev is just every time you go in a full circle. So revs is just 1 cycle. So that means that 1 rev is equal to 2 pi radians. Because a rev is just a revolution. Think about what, like, you going in a whole revolution, a complete circle. And so going in a complete circle in radians is 2 pi. So that's how you can relate the two. So use this relation to convert. Converting you guys already have down, so I'm not gonna go over an example, but of course, on Thursday, if you guys do have questions on that and are wondering like, hey, I need an example, I will provide it and with pleasure. But yeah, so that because we don't need to convert anything for this problem, but I just wanted to explain what the difference was because that always helps me at least like understand what the heck the unit is. So 1 rev is just 2 pi radians. There you go. So let's get on with the problem. I'm gonna delete this, erase all of this stuff. Almost there. Okay. So let's get started with the problem. It doesn't say it on here, but when they talk about merry-go-rounds, they want you to treat it like a disc. So think about, we're looking above the ground. Let me actually insert this right here. Actually, yeah, we can do it like this. Let's not, no, we're just gonna do it like we're looking at the side. So here's the center. We're looking at the side of the merry-go-round. And then, like if we want to make it 3-dimensional. So the merry-go-round, here's like the pole and then all the other stuff that goes around it. Anyways, and then they tell you that there are 3 children riding on it. And they tell you that the 3 children are riding on the edge of the merry-go-round. That means it doesn't matter where the children are at, like with respect to how we're looking at it, they're all at the edge. One of them is here. Another one is, but they're all at the edges. It doesn't matter where they're at. Like the location doesn't matter. Well, the location with respect to the radius does matter, but not the location around the merry-go-round. So the 3 little dots represent each of the people. So let's go. This one's a 22 kilogram. This is the 28, and this is the 30, yeah, kilogram. So this is what we have initially. And so what they tell us is that I'm gonna lasso this so I can copy it and give us the second scenario. I clicked the wrong thing. Paste. And so see, we're gonna be using conservation of energy, conservation of angular momentum for this problem. And how we know how to split it up is once we notice that there is a change in inertia. So the reason why there's a change in inertia in the second scenario is that they tell us that if the child who has a mass of 28 kilograms moves to the center of the merry-go-round. So here we go. Let's erase this and this. Ugh, not the whole thing. Oh, I'm gonna try to do this really carefully. Yay, I did it. If the child is now here in the center, I'm gonna put 28 up here. How does that affect the whole situation? So the inertia changes now. I'm gonna call this inertia 1, inertia 2. Notice I'm gonna call this angular momentum, and then this is gonna be angular momentum prime. Because they're the same. Because of conservation of angular momentum, even if the inertia changes of the system, the angular momentum doesn't. It stays the same. The value of it, the total, equals the same no matter what, as long as there isn't any external force acting on it. Like something doesn't come and like stop it completely, right? So what this tells us is that the regular angular, for the first case, has to equal the angular momentum for the second case. Okay. The only thing we know is that the total inertia for the first case is different from the second, because now you have a person coming closer to the center. And if they come closer to the center, their radius is going to change. The equivalence to this is a figure skater. The first scenario can be figure skater with arms out. And the second scenario, one person came in, so they kind of brought a lot of their mass towards the center. So when mass starts moving towards the center of that rotation axis, the moment of inertia decreases. It gets smaller. And so let's see. They give us a few pieces of information. They tell us what so RPM, this is your omega right here. And that's all the information we're given. So let's write that down. Omega is equal to 20 RPM. And the question is asking, after that child goes into the center, what is the new angular velocity in RPM? So we're trying to find omega, or the angular velocity for this case, the second case. So that means we're looking for omega prime. See, I'm prime because everything down here is prime. That's the whole. So we're looking for this. What is that? How do we even find it? And so that's why I wanted to do this problem, to walk you through a more complex scenario of using angular momentum and knowing how to apply this. If you guys can understand how to do this, anything easier than this is going to be a walk in the park. So let's get to it. The way we want to treat this problem, first we're going to look at the first case, the non-primed angular momentum merry-go-round. And we want to get the angular velocity, or sorry, I'm mixing up all the terms now. You want to get your angular momentum for each individual object on its own and add them all together. It's kind of like conservation of momentum. The total momentum before and after. The first case, you look at the two objects that are moving and you add their momentums together. Here, you're adding the angular momentum of 1, 2, 3, and 4. The merry-go-round is the fourth object. So they all have some angular momentum because they're all spinning. So for the first angular momentum, we're going to have 1, 2, 3. Let me do this one, 4. There we go. We're going to have 4 different cases. So here's the thing. Objects that have all their mass in one location, you treat those as point masses. And so I know right now this makes no sense. You're like, what the heck does that mean? But it will in a little bit, because the merry-go-round by itself, you cannot treat it like a point mass because it has a specific shape to it. It has a lot of mass distributed along a longer distance, unlike the people. The people, in comparison to the merry-go-round, are just on a point basis. And so when you understand the difference between something having a point mass and something not having a point mass, then you can start to get the moment of inertia for each object and how they differ. So when you have a point mass, the moment of inertia is defined as simply mass r squared. So we talked about this in the last problem with the figure skater. This is what the angular moment, what the moment of the rotational mass, the moment of inertia is for a point mass. So this equation is going to apply for each of the people in the merry-go-round, but it's not going to apply for the merry-go-round. And so with that, let me introduce this idea. So I'm going to show this image right here. That's not what I wanted to do. Okay, text mode right here. Let's bring this up here. Okay, so hopefully you guys can all see this right here. And so The idea is that each object, depending on its shape, is going to have a different type of moment of inertia. The principle is still the same. It's mr squared, but the factor in front of it, or what I called earlier the coefficient, is going to be different. Depending on the shape of each object, you're going to have a different moment of inertia. And so you can see, and it gets really intricate because it also depends on where even the same object, but if it's spinning on a different axis, it has a whole different moment of inertia, or at least a different coefficient. And so I want to let you guys know that you shouldn't worry. For the assignments you have going on, you do need to find this information because you have the book and everything. But for exams, I will provide that information. So I'm not going to expect you guys to memorize it or even waste space on your equation sheet to write all that down. I'll give you that information. So, because I don't really care about you memorizing them, I just want you guys to understand that just because the way things are shaped, they have a different moment of inertia, because as they're spinning, if something has more matter in the center than outside, it's going to spin slower or faster depending on the distribution of the matter. If it's a long rod, it's going to spin slower or faster depending on the axis or everything, all of these things. So you can see these different situations right here. So when you're talking about something that you can take as a point mass, like a person on that merry-go-round, then you just use this first equation. But if the object stretches out and has material all across whatever distance is covering, like the merry-go-round, you need to have an understanding of what the moment of inertia is for that merry-go-round. Okay, so I said too much. Let's start writing. So we have 4. We have the angular momentum for, I'm going to put M for merry-go-round, plus we have the angular momentum for the person with 22 kilograms of matter, plus we have the angular momentum for the 28, plus angular momentum for the person with 33. So that's how you want to treat them. You look at all the objects in the situation and you look at all of the people or things that are spinning around. One is the merry-go-round. It's rotating, so it has angular momentum. All the people on the merry-go-round are spinning too, so they have momentum, angular momentum. So we know what the equation for angular momentum is in terms of inertia. So it's going to be omega. So it's going to be inertia for that merry-go-round times omega. So all of these are on the same object. So however fast they're spinning, they're all spinning at the same rate. It's like you in a car when you're driving, your velocity is the same as the car's velocity because you're in the car and it's pulling you at that same rate. So all of these have the same angular momentum. I mean, angular velocity. Sorry. I keep interchanging all these words. Angular for 22 omega plus I for 28 omega plus I for 33 omega. Okay, you get the picture. It starts to stretch out because you have so many things to have to account for. We know that omega is the same for all of them. So we're going to pull that out. So I'm going to do this omega. And now you have the inertia for the mass. I mean, for the merry-go-round, sorry. Inertia for 22 plus inertia for 28 plus inertia for 33. Remember, this is just the before the one person changes the location and changes the whole moment of inertia, the total. So you may be wondering, how do I calculate each I? So we're going to use those equations. So here's the one I'm going to give you guys. The moment of inertia for the merry-go-round is 1 over 12. I think it's over mr squared. Let me just double check that because, see, I don't have them memorized. Disk inertia. You can always just type that out. I just like, hey, what's the moment of inertia for a disk? And so you can always go to images and just see like whatever equations people put up. What is it? I think it's 1/2. Yeah. I don't know why I put 112 1/2. It makes sense because it should have the same inertia as a cylinder that's rotating like that, because if you just segment the cylinder, it gives you that disk, and they should have the same moment of inertia. But that's a whole different thing. So I haven't really gone too much into the theory. I tried to go more into the practicality of this stuff because I think that's more useful. And I know like you guys might be like super overwhelmed right now, but just know this is one of the harder problems. And the reason I'm starting off with this is because if you guys can understand this, or at least part of it, like anything else is just simpler. I rather over prepare you guys than under. If I give you guys something easier, if something harder comes out on the exam, you guys are going to be like, what the heck, prof? And then that's going to be on me. So I know your capability. Like, honestly, you guys are like really good class. Like, in terms of, I always notice this, summer classes are always like on top of their game. So you guys are definitely there. So the moment of inertia for the merry-go-round is this 1/2 mr squared. So merry-go-round, the disk has a factor of 1/2 in the front. That's the only difference. The others are just point masses. They're going to be, oh, sorry, not 1/2. It's just mr squared plus mr squared. So the masses are different. So I'm not, because it's too much notation, but I'll keep track of which one's where. And also the radius. Okay. So like that. The rest of them have point masses because all their masses are concentrated at a certain radius from the merry-go-round, from the center. So you can always just treat people on an object like that as point masses. That's going to be like the rule of thumb. So omega's right there. Okay. Let's start plugging in everything. Actually, should we? Yeah, let's start doing it. So we know the merry-go-round is 100 kilograms. So I'm gonna get rid of this now. We don't really need that. But this is just to show you guys different, how everything has different moments of inertia. So the merry-go-round is 100 kilograms and the radius is 1.6. So that's how you determine the radius for the merry-go-round, is however long it spans. So 100 kilograms times 1.6 squared. Okay, all of that's multiplied. Don't forget, I'm gonna make bigger brackets because you have omega here. Plus, then we have the mass of the first, so it's the first one is the 22. Let me just do this for association. So all of these children are at the same distance away from the center of the merry-go-round. They're the whole 1.6 because that's how far they are. They're at the edge of the merry-go-round. So that's the radius, 1.6. But the only thing that differs is the mass. The mass for the first one is a 22 times r squared, 1 times 1.6 squared, plus the mass of the second, 28 times 1.6 squared. See, that doesn't change, plus 33 kilograms times 1.6 squared. Feel free to rewind this to do whatever you need in order to kind of, if there's something you missed or something I felt like I didn't explain properly, maybe just going back to this. If not, feel free to comment below or email me, or office hours, whatever helps you, like whatever helps you click these, whatever helps these concepts click quicker. You can tell I'm not all there. It's been a long day. But 1, 2, 3, 4. We have the 4 terms, so we're ready. So we know what the angular velocity is. It's 20 RPM. We're not going to change it to rad per second because our answer needs to be in RPM. So it wouldn't make any sense to convert and then have to convert back. So 22, sorry, I have to look at it again, 20 RPM. So 20 RPM. And then all of this is just a number. We can just plug it in. Let's just do that. I'm gonna use my Google calculator. And let's figure this out. We're gonna get an answer. Just always make sure you guys put parentheses around everything, and like, because sometimes that's where, like, for the exam, a lot of issues were because of that. And I'm like, the 0.5. I make these mistakes too. Times 1.6 squared. So I'm gonna put parentheses over all of this. Plus 22 times 1.6 squared. And also don't forget the squared. Like, there's so many values, you want to make sure you have everything intact. 28 times 1.6 squared. And then we have one last one. It's 33. So as I'm doing this, I'm also including parentheses and just making sure I have extra parentheses. Okay. And then parentheses, parentheses, parentheses. I'll put one extra parentheses. Sometimes, yeah. Okay. And then submit this. I'm just double checking it. And then we get an answer. We get, so everything in the big brackets is equal to, once my pen starts acting normal, 300. Oh, that's nasty. And 40. .48. Apologies for the craziness. There's just lag. I changed to my other tablet and I'm still getting this crazy lag sometimes. So it's a pain, but I hope it's not interfering too much for you all. Okay. So 20 RPM times 340. And so all of this is inertia. You're just adding it up. So this is the total inertia for the first case before that one person comes in. So now we have this. That has to equal to the angular momentum of the second case, prime. So now let's get onto that one. So see, it's here. We just calculated this side. Now we have this other side to do. So here we have, so likewise, we're gonna have 4 objects. I'm gonna skip this first part. I'm just gonna go straight into the second one where I pull out the omega. So we know angular velocity, angular momentum, I'm just confusing everything now, is moment of inertia times, and this is the total, so I'm gonna put total, times omega. So I just need to figure out the 4 moments of inertia. Once this starts giving me 2, 3, 4. Okay, and all of that's gonna be times omega. We're trying to solve for this one. This is omega prime. Okay, so let's look at them. If we have all 4 of them like that, you can have them written down the same way. 1/2 mr squared plus mr squared plus mr squared plus mr squared. Okay, so you would plug in the same thing. Like, I'm just gonna plug it into a calculator. No need for me to rewrite all of this, but I do want to mention a few things, because so this would be 100. The radius is still the same. The merry-go-round has not changed radius. It's still going to be 1.6. It's going to look the same as this. Everything's pretty much going to look the same, except for the one person that changed. That one person was a 28 kilogram person. They moved to the center. So what happens if you move to the center? It's similar to torque. When you have a force with 0 radius, you don't have a torque because you're not turning it. You're on that pivot point. You're just pushing on the pivot. You're not pushing at the thing that rotates. You're pushing on the hinges, so to speak, of the door. The hinges isn't gonna make the door move. So if the 28 kilogram person moves there, the 28 kilogram would be the second one, this one right here. So this would be 28 kilograms times the radius, and the radius is 0. 28 times 0 squared, because the person is right in the center, so they don't have any radius distance away from the 1.6 meters of radius that the merry-go-round has. So what that means is that all of this just cancels out. I mean, not all of it, just this one. So that means what changes in the inertia before the 28 kilogram person moves to the center is just the fact that the 28 kilogram person going into the center removes his moment of inertia. I mean, it removes his angular momentum, sorry. Yeah. I mean, also his inertia because he has 0 now, if you assume it's right in the center. So what that does is it just leaves 3 different things now to take into account: the merry-go-round, the 22, and the 33 kilogram person. That's it. So I'm gonna just plug it onto a calculator and see what I get. So all I have to do is just delete the 28 kilogram stuff, and it makes it easy. So now when I calculate this, the total inertia for this case is going to be, once this thing stops acting up. All of this is going to be equal to 268.8. And of course, the units, kilograms per meter squared. Times, so all of that is multiplied times omega prime. That we're trying to solve for this. So now you can see where we're going with this. We're just gonna make this equal to that. So we're gonna have 20 RPM times 340.48. All of that is equal to 268.8 times omega squared. Now we divide that to the other side and we end up getting omega prime is equal to, so now I'm gonna plug that into my calculator. So 20 times 340.48 parentheses, all of that divided by 268.8 gives us omega prime of 25.3 RPM. See, we needed our answer in RPM. That's why we didn't have to convert. We got that. And that makes sense, right? If you think about it, the RPM needs to be bigger because when more material comes towards the center, you have less inertia. If you have less inertia, that means the object should spin faster. So try to use that logic too to double check if your answer is right, or at least in the, like, if you get an answer that's below 20, then you're like, okay, there's something wrong with the math. So that's how you do these type of problems. I know this one was a pain in the butt, but others will be easier. If you have any on the practice, it'd be like that cake. But anyways, that's that with conservation of angular momentum. That's how you treat these problems. Okay, so I'm gonna quickly talk about this next idea and then we're gonna do this problem. We are talking about rotational situations. And we've already discussed how we can, like, all of the stuff we've covered and how I introduced this concept of angular momentum and of inertia. So I say moment of inertia or inertia. It's the same thing, by the way, just letting you guys know, because I know I say it and I just want to make sure you guys realize that it means the same thing. Moment of inertia or inertia, same difference. I hope the main takeaway is understanding why I chose the people to be point masses as opposed to the merry-go-round. You cannot make that a point mass because its whole mass is distributed across a long distance, so it wouldn't make any sense. And because of that, you have to have a different factor in front of its inertia. So from talking about this whole idea of rotation, another big concept covered in this chapter is understanding how you can relate. So I know, bringing back old stuff. So we talked about kinematics, right? So now there's some concept on here about, because it's all about rotation, about looking at kinematic equations and translating them into their rotational counterparts. So we already know how to go from linear to angular ideas, angular from position, displacement or position to angle, from velocity to angular velocity, and from acceleration to angular acceleration. So knowing that, there's this really cool chart I like to use. So I'm going to put this up for you guys. And this should help give a contrast between the two. So what's normally like straight lines up and down is called translational or linear, so whatever. And what's rotating is called rotational. And so these are the three equations in a more simplified way. The number one, the one that I always put on top is this one in the middle. The delta is just they get the initial position and move it to the other side. That's why it's still the same equation. It's just written slightly different. So just FYI. And the other one, this is the one with just no time dependency. This one doesn't have any position dependency. I'm trying to see if it has any other yeah. And so what you see in the rotational is just how you write these equations when you're relating it to rotational situations. If you guys remember how to write the first three kinematic equations from a long time ago, all you have to do is replace the value of, just say, velocity with angular velocity, position with theta with angular position, and so on and so forth. So you can see how they relate. Velocity is just omega, velocity initial is just omega naught, the same thing, and acceleration is just angular acceleration. The only thing that doesn't have a rotational counterpart is time, right? Of course, that just wouldn't make any sense. How do you have rotational time? So that's how you look at these equations. Of course, you can just write these and have these down in your equation sheet. I highly recommend that. But also try to find the analogy between them, because that makes solving these type of problems really easy, because they're not that difficult, but because of the new way of looking at it, because it's rotational, it can get difficult. And so I have an example I'm gonna do, and after that, we're gonna call it. So suppose a piece of dust finds itself on a CD. If the spin rate of the CD, so they already give you the angular velocity, because you can see, you look at the units, that helps us figure out what. So units are going to be really important here to understand what the heck we're looking at. If it's like like in counterpart to velocity and acceleration, like, okay, is this angular velocity or is it angular acceleration, or is it angle, just an angle? So 500 RPM is an angular velocity. It's omega. So they tell you that if the spin rate, the CD is spinning that fast, and the piece of dust is 4.3 centimeters from the center. So like not in the center, but 4.3 centimeters. Remember, centimeters. We're gonna need to convert that to meters. What is the total distance traveled by the dust in 3 minutes? Ignore acceleration due to getting the okay, yeah. So you're just looking at the situation as the CD has been rotating at 500 RPM the whole time. So let's just insert images, always help. Something like that. Looks really similar to them. merry-go-round. So here's where the CD is spinning from. The dust particle fell. We don't know how big the CD is, but that doesn't matter. We just know that the dust fell somewhere right here, and that distance is 4.3 centimeters. Okay. So we're going to be using the rotational equations, and what we're trying to find is what is the total distance traveled by the dust in 3 minutes. So our answer needs to be in position and distance. And so that might seem really confusing because you're like, wait, like, how do I even begin this? Do I actually start with the linear equations? And what I say is never start with the linear equations. Once you get, so, okay, here's how I would recommend you look at it. Whatever you're trying to find, we're trying to find position. If your scenario is in the rotational case, like here, like you have angular velocity, it's a lot easier to use the rotational equations and find the rotational counterpart first. So if we're looking for position, we're going to need to use an equation where we can find angular position, so theta. Okay, that's how I would highly recommend to always work these problems if that's the case. If you're just looking for theta, then you avoid that extra step. So here, there's only 2 equations with theta, the second one and this third one. And so this is technically the first one when I write them out. So we have these 2. You can only use these 2 because these are the only 2 with theta. Okay. So how do we choose which one to use? Then we have to look at them. Okay, let's start with the last one. We don't know what the final, so this one wouldn't really get us anywhere because there isn't any acceleration or angular acceleration to this problem. So if alpha was 0, then that eliminates theta, and then we can't even solve for it. So that means we have to rely on what I normally write as the first equation, but was written as like the second equation here. So normally how I would write it is like theta, theta final is equal to theta, oh my goodness, this thing, theta initial, so not plus omega not t plus 1/2 alpha t squared. So what they did is they subtracted theta naught to both sides. And we know that when you have a little triangle in front, which is called delta theta, it's theta final minus theta initial. Let's fix this a little bit. There we go. And that's what you have. You have theta minus theta initial. So that's why they have a change in theta. And I think it's easier because in reality, this is what you're trying to solve for. Delta x, like how much distance was covered, that displacement of position. Because either way, this is going to be 0. Because if you start at 0 and it starts spinning, what is the total distance covered? But of course, we're finding the angular distance right now, and then we're going to convert that to actual like linear distance. Okay. So we'll keep it how this is written. Theta is equal to that plus 1/2 alpha t squared. This problem says that ignore acceleration. So boom, that means there's no acceleration. It's 0, crosses out. We're only dealing with this now. We're trying to solve for this. So we know what the angular acceleration is. It's 500 RPM. I'm going to keep the units because if it turns out that I need to convert, then I will, because I'm not sure if I have to, times time. And then this is theta change in theta. Are we given the time? So they do. They tell us what is the total distance traveled by the dust in 3 minutes. So 3 minutes. Let's rewrite 500 RPM in like fraction format so we can see if we need to convert, because RPM has it in minutes. So it's a angular velocity in minutes instead of like radians per second. So 500 rev per minute. So because this is in minutes, your time, you don't want to convert 3 minutes. Keep 3 minutes in minutes. So plug in 3 and put minutes. Because you can see that's going to cancel out the minutes. If you have it in seconds, that's not going to cancel out with the minutes. This will though. So I did not convert the 3. So when you're doing these problems, keep an eye on your units. If your time is in seconds and you need to get the answer in rads per second, make sure to convert. If not, like here, we started doing this. It turns out we don't really need to convert just yet. We might have to, but once we get there, we'll get there. Okay. So that means 500 times 3, we're going to get 1,500 revs. Okay. So we have all of this in revs. So this is our theta. Okay. So now that we're here, this is the answer we want to get to. We got this. So we need to now go from theta to position. How do we do that? So remember those equations we talked about like last week or 2 weeks ago? I forgot. So to relate linear position to angular position, all you have to do is define, you can just get these equations, change. So you can just do it like that. So there's these equations. Oh, my bad. I'm like, wait, there's something out there wrong. Radius. Let me redo that because I'm going to put capital R just so it's easy to see. So it's like that. Yeah. Over radius. And the same thing for acceleration. So, I mean, of course, if you have theta, you can just put X, R, omega, velocity over R. So that's how you relate the counterpart. Like when you want to have a relation between the linear and the angular, it's just divided by a radius. So we have our theta. You can plug it in, or so that's what we think. And we have the radius. The radius is 4.3 centimeters. But here's the thing. Our answer is in revs. If we want to get our answer, let's see, what do they want? What is the distance? Yeah, what is the total distance? Okay. We need to have consistent units now. So what I'm good, because look, we have centimeters. We might wonder, what are like the equivalent units for revs and distance? Is it inches? Is it, what is empirical system? So we need to convert from revs to radians. We want to just change everything to standard units now, just so when we get our distance, it's good. It's going to be in meters. So how do we convert 1,500 revs to radians? Remember, one rev is equal to 2 pi radians. So I have to put revs in the denominator. So 1 rev is equal to 2 pi radians. So this is a lot of unit conversion. Like, just keep track of it. Hopefully you don't get like, I mean, for exams, I'm not going to be this intense. Like usually everything might already be converted. Maybe like certain little things you have to convert, but nothing like where like you have to really like, just as long as you understand how to get here instead of like the little nitpicking stuff, that could be more important. So this cancels out. So our theta is not radians. We have it in standard units. Let's go with that. Let's plug that into, actually, I'm just gonna keep it in radians for right now. I'll plug everything at the end. So okay, I can use this. Let's use that one. I mean, it's all the same thing. I just need the proportionality, but let's use this equation. Just so because I don't want to like get any confusion. I want to make sure we go step by step. So let's plug everything into this equation now. So 1,500 times 2 pi radians, that's going to give us 3,000 pi radians. That is equal to, we're trying to solve, this is what we're trying to solve for, divided by our radius. Our radius is 4.3 centimeters. In meters, that is, so centimeters 100, so 2 decimal places. So it's gonna be 0.043, because the decimal is in front of the 4, and then 1, 2. So there we go, meters. Cool. And so now we can multiply this to both sides to solve for delta x, for how much distance it covered as it was spinning in the CD with that given speed. So 3,000 times pi times 0.043 meters. That will give me an answer of, and see, the reason why I had to convert from revs to radians is because if we did all of this, our final answer would still be in revs times meters, but because radians is implicit with meters, it's part of the same system, then our answer is just in meters. Like radians is like just hiding behind there. So it's part of the same system. So it's gonna give us the right answer. It doesn't overshadow the meters. It's not like its own separate unit. Once meters is there, it replaces it. But with revs, it doesn't replace it. So just make sure to associate radians to standard units. So if you do have revs and you want your answer in standard units, convert to radians, sorry. So our final answer, after multiplying this to that side, we get 405. I'm gonna keep it at 3 digits, meters. Boop. So that dust travels that much distance. Like if you were to measure it with the tape, how many ever times it goes in a circle, that's the linear distance it covers. The angular distance, of course, 1,500 revs before converting, that means that the disk traveled 1,500 times as the dust was on there. And so converting it to radians is harder to perceive, but that helps us get the proper units. So that's how you do these problems. Whatever you're looking for, start with that equation, use all the rotational ones. And if you need to get an answer in linear format, or how they call it here, translational format, make sure you understand how to do the different conversions, either with theta, omega, or alpha, if you're talking about angular acceleration. Okay. But it's the same idea, like you have your concepts and you just plug them in the equation, whatever you're given. Okay, I know that was a lot, but I really just wanted to have all of this down so you guys can look at this video whenever, recap it, because this will be like, these concepts will be on the exam, like guaranteed. So study them up, look at the problems from the practice quiz, from the real quiz, and understand these concepts. Ask me questions if you have them. I really want to help you guys out as much as possible with and if you guys look at this before the practice exam that we're having this Thursday, that's going to help you like at least grasp the concepts a little bit more, so then you can see other problems similar to that and just kind of like get the ball rolling and understanding what's going to be on the test and how to study for it, and maybe have the understanding of these concepts too. Okay, so with that being said, I'm going to stop sharing this. Thank you guys so much. Sorry for the longness. Yeah, and apologies again for the absence ooh, I ain't trying to burden none of you guys with that, but sorry for that whole situation. I hope you guys are doing well. Please leave comments if you have them below, or email me. Or if you have any other questions outside of this, please email me. Like, I really appreciate your guys' comments, because sometimes there's things I really like. I'm like, oh, okay, yeah, explanation. I really try to be as open as possible with everything I do. But of course, there's times where it might seem like I'm not. So I would appreciate that, so then I can elaborate and explain. Thank you so much. I'll see you guys on Thursday. We're seeing this after. Then good luck with the exam. You guys got this. Okay, bye everyone.